Good morning, students. In the last lecture, we discussed about the state variables which represent the thermodynamic system. We also see what are the intensive variables and extensive variable, and we also learn about the thermodynamic equilibrium. If the thermodynamic system must be in thermodynamic equilibrium, then it should be in mechanical equilibrium, in chemical equilibrium, and in the thermal equilibrium. So today we are going to see a very important topic, which is nothing but the equation of the state. Now we know that every thermodynamic system can be completely described by the state variables. Which are the state variable? Pressure, temperature, volume, mass. These are the state variables which can be used to describe a thermodynamic system. But always is this thermodynamic system in thermal equilibrium? No. Sometimes in such processes, thermodynamic system is not in the equilibrium state. So, for example, when a football gets punctured, there is a sudden change between the volume and the pressure of the football as well as of the air. So, in this sudden change, the thermodynamic system is not in the equilibrium. As well as when a petrol inside the vehicle burns and converted into steam, these processes happen suddenly, and therefore the sudden change is due to the thermal or the equilibrium of the thermodynamic system. So we can say that when such type of sudden reactions are happened, the system is not in the thermal or in the thermodynamic equilibrium. Now when the time passes, as the time passes, the air which is passed through the atmosphere, this process also get come to the equilibrium, as well as when the petrol converted into steam, this process also take some time and come into the equilibrium. So after some time, all thermodynamic processes can attain the thermodynamic equilibrium. Now the mathematical relation, what is equation of state? Let's see here. What is equation of state? The mathematical relation between state variables is called equation of state for the thermodynamic system. If a question is asked in the examination, what is the equation of state? So you can define this equation of state as the mathematical relation between the state variables is called the equation of state for a thermodynamic system. Now, what is the example? The simple example, we all know that the ideal gas equation. What is ideal gas equation? Ideal gas equation is the PV is equal to nRT, where this P, V and T, they are the state variables which completely describe the condition or the equilibrium condition of the system. This is pressure, volume, this N is the number of moles, this R is a constant, gas constant, and this T is the absolute temperature. So this equation is called the equation of state for the ideal gas, in which this P, V and T, they are only three state variables, because here this n is the number of moles which is kept constant and this r is a gas constant. So there are three state variables P, V and T in this case. This equation is for ideal gas, but if we consider real gas, the equation becomes very complicated. Okay, so for the ideal gas, you can write the state equation like this, but in the case of real gas, this equation changes by some amount. Okay, now we know that in this equation there are three type of combinations are possible. Which are the combinations? For example, we can write PV, we can write PT, and we can write VT. If, what is the condition? If the number of moles are kept constant. If the number of moles of ideal gas kept constant, then we can state the graphical representation between pressure and volume, pressure and temperature, and volume and temperature. Okay, now let's see the example PV diagram. It is also called as a pressure volume indicator. So we can write the PV diagram. So what is the PV diagram? This is the graphical representation of pressure versus volume. So we can write here, we can draw here. This is volume and this is pressure. So how the ideal gas behave when their pressure and volume both changes? Okay, so we know that pressure and volume, they are inversely proportional to each other, because at a constant temperature, this term become constant and this PV is equal to constant. And if PV is equal to constant, it means pressure and volume, they are inversely proportional to each other. So for example, this is the initial value of pressure P1 and this is the initial value of volume V1. Okay, now this is P1 and this is P2. So how we can write this equation? How we can draw this equation? So here we are seeing the PV diagram. In our book, they are given a such diagram 4.11a, in which we can write here P1 and P2. Okay, and here we can write V1 and V2. Okay, so we know that when the pressure is more, the volume is less. So we can draw a point here, and this P2 and P2. So here we can show this PV diagram like this. So this is like, so this is the shaded area which show the work done during the process. Okay, now this is the case arises when this case arises when the work done is positive, and work done is positive in the case of expansion. So when the expansion takes place, volume increases from V1 to V2, then pressure decreases from P1 to P2, then this shaded area denotes the total work done, and in the case of expansion, the work done W is equal to integration of V1 to V2 P dV is greater than 0. In the case of expansion, work done is always equal to, or it is always greater than 0. In such cases, the ideal gas follows such type of graph. This is the graph for the expansion when the volume changes from V1 to V2. Now we see this PV diagram in the case of compression. in the case of compression. What happens in the case of compression? We draw a simple diagram here. This pressure and this is volume. In the textbook page number 85, it is given 4.11b. So here this is P2 and this is P1. This is, what is this? This is V2 and this is V1. Okay. So as we know, pressure and volume, they are inversely proportional to each other. So what is the graph? The graph is like this. Again, this is the point for P2 V2 and this is the point for P1 V1. So the graph, the nature of the graph is like this. Okay. So if we draw here and like this, here and like this, then this shaded area denotes the work done during the compression. What happened during the compression? What happens? This work done, W, is equal to V1 to V2 P dV, which is less than 0. Okay, in the case of compression. Now, third case is if the pressure kept constant. If the pressure kept constant and let the volume changes, so how we can represent the PV diagram? So the PV diagram can be represented as, this is the pressure and this is volume. So pressure is constant, so pressure can be represented by a straight line, and for example the initial volume is equal to V1 and the final volume is equal to V2. So we can write here the shaded area is the work done and this work done is equal to, what is equal to? It is V1 to V2 P multiplied by dV. Okay, which is equal to P multiplied by V2 minus V1. In the case of pressure is constant, so this pressure remains constant, then this pressure axis, this axis is parallel to the volume axis. Okay, as we see this volume is increases from V1 to V2 but the pressure remains constant. So in this way, what is the equation of state? Equation of state is, it is the mathematical relation between the state variables which represent the condition or the thermodynamic equilibrium of the thermodynamic system. So in this case, in this lecture, we discuss about the equation of state and simple example of PV diagram which indicate the behavior of the gas under the pressure and volume. As the pressure changes, volume changes. Our condition we taken here that the pressure remains constant and volume get changes. So in the next lecture we are going to discuss about the thermodynamic processes. What are thermodynamic processes? We are going to see in the next lecture. So this is for today. Thank you. Have a nice day. Bye.